The Unified Extensible Firmware Interface is a specification that defines a software interface between an operating system and platform firmware. UEFI is meant to replace the basic input-output system firmware interface, originally present in all IBM PC-compatible personal computers. In practice, most UEFI images provide legacy support for BIOS services. UEFI can support remote diagnostics and repair of computers, even without another operating system. The original EFI specification was developed by Intel. Some of its practices and data formats mirror ones from Windows. In 2005, UEFI deprecated EFI 1.10. The UEFI specification is managed by the Unified EFI Forum. History: the original motivation for EFI came during early development of the first Intel Euro HP Itanium systems in the mid-1990s. BIOS limitations were unacceptable for the larger server platforms Itanium was targeting. The effort to address these concerns began in 1998 and was initially called Intel Boot Initiative. It was later renamed to EFI. In July 2005, Intel ceased development of the EFI specification at version 1.10, and contributed it to the Unified EFI Forum, which has evolved the specification as the Unified Extensible Firmware Interface. The original EFI specification remains owned by Intel, which exclusively provides licenses for EFI-based products, but the UEFI specification is owned by the Forum. Version 2.1 of the UEFI specification was released on January 7, 2007. It added cryptography, network authentication and the user interface architecture. The current UEFI specification, version 2.4, was approved in July 2013. Advantages: the interface defined by the EFI specification includes data tables that contain platform information, and boot and runtime services that are available to the OS loader, and OS UEFI firmware provides several technical advantages over a traditional BIOS system: ability to boot from large disks with a GUID partition table, CPU-independent architecture, CPU-independent drivers, flexible pre-OS environment, including network capability, modular design, compatibility, processor compatibility. As of version 2.4, processor bindings exist for Itanium, x86, x86-64, ARM and ARM64. Only little-endian processors can be supported. A normal PC BIOS is limited to a 16-bit processor mode and 1 MB of addressable space due to the design being based on the IBM 5150, which used the 16-bit Intel 8088. In comparison, the UEFI processor mode can be either 32-bit or 64-bit. 64-bit UEFI understands long mode, which allows applications in the pre-boot execution environment to have direct access to all of the memory using 64-bit addressing. UEFI requires the firmware and operating system loader to be size-matched. For example, a 64-bit UEFI implementation can only load a 64-bit UEFI operating system bootloader or kernel. After the system transitions from boot services to runtime services, the operating system kernel takes over. At this point, the kernel can change processor modes if it desires, but this bars usage of the runtime services. As of version 3.15, Linux kernel supports booting of 64-bit kernels on 32-bit UEFI implementations running on x86-64 CPUs, with UEFI handover support from a UEFI bootloader as the requirement. UEFI handover protocol deduplicates the UEFI initialization code between the kernel and UEFI bootloaders, leaving the initialization to be performed only by the Linux kernel's UEFI boot stub. Disk device compatibility. In addition to the standard PC disk partition scheme, which uses a master boot record, UEFI works with a new partitioning scheme, GUID partition table. GPT is free from many of the limitations of MBR. In particular, the MBR limits on the number and size of disk partitions per disk are relaxed. GPT allows for a maximum disk and partition size of 8 ZB. The UEFI specification explicitly requires support for FAT32 for EFI system partitions, and FAT16 or FAT12 for removable media. Specific implementations may support other file systems. Linux. Support for GPT in Linux is enabled by turning on the option config EFI partition during kernel configuration. This option allows Linux to recognize and use GPT disks after the system firmware passes control over the system to Linux. For reverse compatibility, Linux can use GPT disks in BIOS-based systems for both data storage and booting, as both Grub2 and Linux are GPT-aware. Such a setup is usually referred to as BIOS GPT. As GPT incorporates the protective MBR, a BIOS-based computer can boot from a GPT disk using GPT-aware bootloaders stored in the protective MBR's bootstrap code area. In case of Grub, such a configuration requires a BIOS boot partition for Grub to embed its second stage code due to absence of the post-MBR gap in GPT partition disks. Commonly 1 MB in size, this partition's globally unique identifier in GPT scheme is 21,686,148-6449-6E6F744E-6565644544649 and it is used by Grub only in BIOS GPT setups. From the Grub's perspective, no such partition type exists in case of MBR partitioning. This partition is not required if the system is UEFI based, as there is no such embedding of the second stage code in that case. UEFI systems can access GPT disks and directly boot from them, simplifying things and allowing UEFI boot methods for Linux. Booting Linux from GPT disks on UEFI systems involves creation of an EFI system partition, which contains UEFI applications such as bootloaders, operating system kernels, and utility software. Such a setup is usually referred to as UEFI GPT, while ESP is recommended to be at least 512 MB in size and formatted with a FAT32 file system for maximum compatibility. For backwards compatibility, most of the UEFI implementations also support booting from MBR partition disks, through the Compatibilities Support module which provides legacy BIOS compatibility. In that case, booting Linux on UEFI systems is the same as on legacy BIOS-based systems. Microsoft Windows, the 64-bit versions of Microsoft Windows Vista and later, 32-bit versions of Windows 8, and the Itanium versions of Windows XP and Server 2003 can boot from disks with a partition size larger than 2 TB. Features, services, EFI defines two types of services, boot services and runtime services. Boot services are only available while the firmware owns the platform. Boot services include text and graphical consoles on various devices, and bus, block and file services. Runtime services are still accessible while the operating system is running. They include services such as date, time and NVRAM access. In addition, the Graphics Output Protocol provides limited runtime services support. See also Graphics Features section below. The operating system is permitted to directly write to the frame buffer provided by GOP during runtime mode. However, the ability to change video modes is lost after transitioning to runtime services mode until the OS graphics driver is loaded. Variable services, UEFI variables provide a way to store data, in particular non-volatile data, that is shared between platform firmware and operating systems or UEFI applications. Variable namespaces are identified by GUIDs, and variables are key-value pairs. For example, variables can be used to keep crash messages in NVRAM after a crash for the operating system to retrieve after a reboot. Time services, UEFI provides device-independent time services. Time services include support for time zone and daylight saving fields, which allow the hardware real-time clock to be set to local time or UTC. On machines using a PCAT real-time clock, the clock still has to be set to local time for compatibility with BIOS-based Windows. Protocols, EFI defines protocols as a set of software interfaces used for communication between two binary modules. All EFI drivers must provide services to others via protocols. Device drivers. In addition to standard architecture-specific device drivers, the EFI specification provides for a processor-independent device driver environment, called EFI bytecode or EBC. System firmware is required by the UEFI specification to carry an interpreter for any EBC images that reside in or are loaded into the environment. In that sense, EBC is similar to open firmware, the hardware-independent firmware used in PowerPC-based Apple Macintosh and Sun Microsystems SPARC computers, among others. Some architecture-specific EFI device driver types can have interfaces for use from the operating system. This allows the OS to rely on EFI for basic graphics and network functions until OS-specific drivers are loaded. Graphics features. The EFI specification defined a UGA protocol as a way to support device-independent graphics. UEFI did not include UGA and replaced it with GOP, with the explicit goal of removing VGA hardware dependencies. The two are similar. UEFI 2.1 defined a human interface infrastructure to manage user input, localized strings, fonts, and forms. These enable OEMs or IBVs to design graphical interfaces for pre-boot configuration. UEFI itself does not define a user interface. Most early UEFI implementations were console-based, but as early as 2007 some implementations featured a graphical user interface. Booting. UEFI booting. The UEFI specification defines a boot manager, a firmware policy engine that is in charge of loading the operating system loader and all necessary drivers. The boot configuration is controlled by a set of global NVRAM variables, including boot variables that indicate the paths to the loaders. Operating system loaders are a class of the UEFI applications. As such, they are stored as files on a file system that can be accessed by the firmware, called EFI system partition. UEFI defines a specific version of FAT, which encompasses FAT32 file systems on ESPs, and FAT16 and FAT12 on removable media. Supported partition table schemes include MBA and GPT, as well as LTORA volumes on optical disks. UEFI does not rely on a boot sector, although ESP provides space for it as part of the backwards compatibility. UEFI booting from GPT disks is commonly called UEFI GPT. Bootloaders can also be automatically detected by the UEFI firmwares, to enable booting from removable devices. Auto-detection relies on a standardized file path to the operating system loader, depending on the actual architecture to boot. Format of the file path is defined as EFI system partition boot machine type short name EFI. For example, boot BOOTX64 EFI. It is common for UEFI firmware to include a user interface to the boot manager, to allow the user to select and load the operating system among the possible options. CSM booting. For backwards compatibility, most of the UEFI implementations on PC-class machines also support booting in legacy BIOS mode from MBR partition disks, through the Compatibilities Support module which provides legacy BIOS compatibility. In that scenario, booting is performed in the same way as on legacy BIOS-based systems, by ignoring the partition table and relying on the content of a boot sector. BIOS booting from MBR partition disks is commonly called BIOS MBR, regardless of it being performed on UEFI or legacy BIOS-based systems. As a side note, booting legacy BIOS-based systems from GPT disks is also possible, and it is commonly called BIOS GPT. Despite the fact MBR partition tables are required to be fully supported within the UEFI specification, some UEFI firmwares immediately switch to the BIOS-based CSM booting depending on the type of boot disk's partition table, thus preventing UEFI booting to be performed from EFI system partitions on MBR partition disks. Such a scheme is commonly called UEFI MBR. Network booting. UEFI specification includes support for booting over network through the pre-boot execution environment. Underlying network protocols include Internet Protocol, User Datagram Protocol, Dynamic Host Configuration Protocol and Trivial File Transfer Protocol. Included is also support for boot images remotely stored on storage area networks, with Internet Small Computer System Interface and Fiber Channel over Ethernet as supported protocols for accessing the SANs. Secure boot. The UEFI 2.2 specification adds a protocol known as Secure Boot, which can secure the boot process by preventing the loading of drivers or OS loaders that are not signed with an acceptable digital signature. When Secure Boot is enabled, it is initially placed in Setup mode, which allows a public key known as the platform key to be written to the firmware. Once the key is written, Secure Boot enters user mode, where only drivers and loaders signed with the platform key can be loaded by the firmware. Additional key exchange keys can be added to a database stored in memory to allow other certificates to be used, but they must still have a connection to the private portion of the platform key. Secure Boot can also be placed in custom mode, where additional public keys can be added to the system that do not match the private key. Secure Boot is supported by Windows 8, Windows Server 2012, and a number of Linux distributions including Fedora, OpenSUSE, and Ubuntu. Compatibility Support Module. The Compatibility Support Module is a component of the UEFI firmware that provides legacy BIOS compatibility by emulating a BIOS environment, allowing legacy operating systems and some option ROMs that do not support UEFI to still be used. CSM also provides required legacy system management mode functionality, called Compatibility SMM, as an addition to features provided by the UEFI SMM. This is optional, and highly chipset and platform-specific. An example of such a legacy SMM functionality is providing USB legacy support for keyboard and mouse, by emulating their classic PS/2 counterparts. The UEFI shell. UEFI provides a shell environment, which can be used to execute other UEFI applications, including UEFI bootloaders. Apart from that, commands available in the UEFI shell can be used for obtaining various other information about the system or the firmware, including getting the memory map, modifying boot manager variables, running partitioning programs, loading UEFI drivers, and editing text files. Source code for a UEFI shell can be downloaded from the Intel's Tino Core UDK 2010/EDK2 SourceForge project. Shell v2 works best in UEFI 2.3+ systems and is recommended over the Shell v1 in those systems. Shell v1 should work in all UEFI systems. Methods used for launching UEFI shell depend on the manufacturer and model of the system motherboard. Some of them already provide a direct option in firmware setup for launching. For example, compiled x86-64 version of the shell needs to be made available as EFI system partition/shellx64 EFI. Some other systems have an already embedded UEFI shell which can be launched by appropriate key press combinations. For other systems, the solution is either creating an appropriate USB flash drive or adding manually a boot option associated with the compiled version of shell. Extensions. Extensions to EFI can be loaded from virtually any non-volatile storage device attached to the computer. For example, an original equipment manufacturer can distribute systems with an EFI partition on the hard drive, which would add additional functions to the standard EFI firmware stored on the motherboard's ROM. Implementation and adoption. Intel EFI. Intel's implementation of EFI is the Intel Platform Innovation Framework, codenamed Tino. Tino runs on Intel's XSCALE, Itanium and IA32 processors, and is proprietary software, although a portion of the code has been released under the BSD license or Eclipse public license as Tino Core. Tino Core can be used as a payload for Core boot. Phoenix Technologies implementations of UEFI include its Secure Core and Secure Core Tino products. American Megatrends offers its own UEFI implementation known as Aptio, while Inside Software offers Inside H2O, its own implementation of Tino. Platforms using EFI UEFI. Intel's first Titanium workstations and servers, released in 2000, implemented EFI 1.02. Hewlett-Packard's first Titanium DO systems, released in 2002, implemented EFI 1.10. They were able to boot Windows, Linux, FreeBSD and HPUX. OpenVMS added UEFI capability in June 2003. In January 2006, Apple Incorporated shipped its first Intel-based Macintosh computers. These systems used EFI instead of open firmware, which had been used on its previous PowerPC-based systems. On April 5, 2006, Apple first released Boot Camp, which produces a Windows drivers disk and a non-destructive partitioning tool to allow the installation of Windows XP or Vista without requiring a reinstallation of Mac OS X. A firmware update was also released that added BIOS compatibility to its EFI implementation. Subsequent Macintosh models shipped with the newer firmware. During 2005, more than 1 million Intel systems shipped with Intel's implementation of UEFI. New mobile, desktop and server products, using Intel's implementation of UEFI, started shipping in 2006. For instance, boards that use the Intel 945 chipset series use Intel's UEFI implementation. Since 2005, EFI has also been implemented on non-PC architectures, such as embedded systems based on XSCALE cores. The EDK includes an NT32 target, which allows EFI firmware and EFI applications to run within a Windows application. But no direct hardware access is allowed by EDK NT32. This means only a subset of EFI application and drivers can be executed at the EDK NT32 target. In 2008, more x86-64 systems adopted UEFI. While many of these systems still allow booting only the BIOS-based OSes via the compatibility support module, other systems started to allow booting UEFI-based OSes. For example, IBM X3450 server, MSI motherboards with Click BIOS, all HP EliteBook notebook and tablet PCs, newer HP compact notebook PCs. In 2009, IBM shipped System X machines and Blade Center HS22 with UEFI capability. Dell shipped PowerEdge T610, R610, R710, M610 and M710 servers with UEFI capability. More commercially available systems are mentioned in a UEFI white paper. In 2011, major vendors launched several consumer-oriented motherboards using the Intel 6 series LGA1155 chipset and 9 Armenian DRAM series AM3 Plus chipsets with UEFI. With the release of Windows 8 in October 2012, Microsoft's certification requirements now require that computers include firmware that implements the UEFI specification. Furthermore, if the computer supports the connected standby feature of Windows 8, then the firmware is not permitted to contain a compatibility support module. As such, systems that support connected standby are incapable of booting legacy BIOS operating systems. Operating systems: an operating system that can be booted from EFI is called EFI Aware OS, defined by EFI specification. Here the term booted from EFI means directly booting the system using EFI OS loaders stored on any storage device. The default location for the operating system loader is EFI System Partition Boot Machine Type Short Name EFI, where short name of the machine type can be IA32, X64, IA64, ARM or AA64. Some operating systems vendors may have their own boot loaders. They may also change the default boot location. The Linux kernel has been able to use EFI at boot times since early 2000, using the ULILO EFI bootloader or, more recently, EFI versions of Grub. Grub plus Linux also supports booting from a GUID partition table without UEFI. The distribution Ubuntu added support for UEFI Secure Boot as of version 12.10. Further, the Linux kernel can be compiled with the option to run as an EFI bootloader on its own through the EFI bootstub feature. HPUX has used EFI as its boot mechanism on IA64 systems since 2002. HP OpenVMS has used EFI on IA64 since its initial evaluation release in December 2003, and for production releases since January 2005. Apple uses EFI for its line of Intel-based Macs. Mac OS X v10.4 Tiger and Mac OS X v10.5 Leopard implement EFI v1.10 in 32-bit mode even on newer 64-bit CPUs, but full support arrived with Mac OS X v10.8 Mountain Lion. The Itanium versions of Windows 2000 implemented EFI 1.10 in 2002. Miss Windows Server 2003 for IA64, Miss Windows XP 64-bit edition and Windows 2000 Advanced Server Limited Edition, all of which are for the Intel Itanium family of processors, implement EFI, a requirement of the platform through the dig64 specification. Microsoft introduced UEFI for x86-64 Windows operating systems with Windows Server 2008 and Windows Vista Service Pack 1, so the 64-bit versions of Windows 7 are compatible with EFI. 32-bit UEFI was originally not supported since vendors did not have any interest in producing native 32-bit UEFI firmware because of the mainstream status of 64-bit computing. Windows 8 includes further optimizations for UEFI systems, including a faster startup, 32-bit support, and secure boot support. There do appear to be some issues with Windows 7 machines not properly supporting the use of MB as data disks as per Microsoft's own implementation specifications. The typical behavior is a refusal to recognize the presence of any operating system to boot from. On March 5, 2013, the FreeBSD Foundation awarded a grant to a developer seeking to add UEFI support to the FreeBSD kernel and bootloader. The changes were initially stored in a discrete branch of the FreeBSD source code, but were merged into the mainline source on April 4, 2014. The changes include support in the installer as well. Oracle Solaris 11.1 and later support UEFI boot for x86 systems with UEFI firmware version 2.1 or later. Grub2 is used as the bootloader on x86. Use of UEFI with virtualization. HP Integrity Virtual Machines provides UEFI boot on HP Integrity servers. It also provides a virtualized UEFI environment for the guest UEFI Aware OSes. Intel hosts an open virtual machine firmware project on SourceForge. VMware Fusion 3 software for Mac OS X can boot Mac OS X server virtual machines using EFI. VMware Workstation unofficially supports EFI, but it needs to be manually enabled by editing the VMX file, and as of 2012 Secure Boot is not yet supported. ESXi vSphere 5.0 officially support UEFI. VirtualBox has implemented UEFI since 3.1, but limited to Unix Linux operating systems. QEMU can be used with the open virtual machine firmware provided by Tinocore. The VMware ESXi version 5 hypervisor, part of VMware vSphere, supports virtualized EFI as an alternative to BIOS inside a virtual machine. Second generation of the Microsoft Hyper-V virtual machine supports virtualized UEFI. Applications Development, EDK2 Application Development Kit makes it possible to use standard C library functionalities within UEFI applications. EADK can be downloaded from the Intel's Tinocore UDK 2010/EDK2 SourceForge project. Even a port of the Python interpreter is made available as a new EFI application by using the EADK. A minimalistic Hello World C program written using EADK looks similar to its usual C counterpart. Criticism: numerous digital rights activists have protested against UEFI. Ronald G. Minich, a co-author of Coroboot, and Cory Doctorow, a digital rights activist, have criticized EFI as an attempt to remove the ability of the user to truly control the computer. It does not solve any of the BIOS long-standing problems of requiring two different drivers, one for the firmware and one for the operating system, for most hardware. Open source project Tinocore also provides the UEFI interfaces. Tinocore lacks the specialized drivers that initialize chipset functions, which are instead provided by Coroboot, of which Tinocore is one of many payload options. The development of Coroboot requires cooperation from chipset manufacturers to provide the specifications needed to develop initialization drivers. Secure Boot. In 2011, Microsoft announced that computers certified to run its Windows 8 operating system had to ship with Secure Boot enabled using a Microsoft private key. Following the announcement, the company was accused by critics and free software open source advocates of trying to use the Secure Boot functionality of UEFI to hinder or outright prevent the installation of alternative operating systems such as Linux. Microsoft denied that the Secure Boot requirement was intended to serve as a form of login, and clarified its requirements by stating that systems certified for Windows 8 must allow Secure Boot to enter custom mode or be disabled, but not on systems using the ARM architecture. Other developers raised concerns about the legal and practical issues of implementing support for Secure Boot on Linux systems in general. Former Red Hat developer Matthew Garrett noted that conditions in the GNU General Public License version 3 may prevent the use of the grub bootloader without a distribution's developer disclosing the private key, and that it would also be difficult for advanced users to build custom kernels that could function with Secure Boot enabled without self-signing them. Other developers suggested that signed builds of Linux with another key could be provided, but noted that it would be difficult to persuade OEMs to ship their computers with a required key alongside the Microsoft key. Several major Linux distributions have developed different implementations for Secure Boot. Matthew Garrett himself developed a minimal bootloader known as shim. A pre-compiled, signed bootloader that allows the user to individually trust keys provided by distributors. Ubuntu 12.10 uses an older version of shim pre-configured for use with Canonical's own key that only verifies the bootloader and allows unsigned kernels to be loaded. Developers believe this practice of only signing the bootloader is more feasible, since a trusted kernel is only effective at securing user space and not the pre-boot state. This also allows users to build their own kernels and use custom kernel modules as well, without needing to reconfigure the system. Canonical also maintains its own private key to sign installations of Ubuntu preloaded on certified OEM computers that run the operating system, and also plans to enforce a Secure Boot requirement as well, requiring both a Canonical key and a Microsoft key to be included in their firmware. Fedora also uses shim, but requires that both the kernel and its modules be signed as well. It has been disputed whether the kernel and its modules must be signed as well. While the UEFI specifications do not require it, Microsoft has asserted that their contractual requirements do, and that it reserves the right to revoke any certificates used to sign code that can be used to compromise the security of the system. In February 2013, another Red Hat developer attempted to submit a patch to the Linux kernel that would allow it to pass Microsoft's Authenticode signing using a master X509 key embedded in PE files signed by Microsoft. However, the proposal was criticized by Linux creator Linus Torvalds, who attacked Red Hat for supporting Microsoft's control over the Secure Boot infrastructure. On March 26, 2013, the Spanish free software development group Hispalinux filed a formal complaint with the European Commission, contending that Microsoft's Secure Boot requirements on OEM systems were obstructive and anti-competitive. At the Black Hat conference in August 2013, a group of security researchers presented a series of exploits in specific vendor implementations of UEFI that could be used to exploit Secure Boot. Firmware issues. The increased prominence of UEFI firmware in devices has also led to a number of technical issues blamed on their respective implementations. Following the release of Windows 8 in late 2012, it was discovered that certain Lenovo computer models with Secure Boot had firmware that was hard-coded to only allow executables named Windows Boot Manager, or Red Hat Enterprise Linux to load, regardless of any other setting. Other issues were encountered by several Toshiba laptop models with Secure Boot that were missing certain certificates required for its proper operation. In January 2013, a bug surrounding the UEFI implementation on some Samsung laptops was publicized, which caused them to be bricked after installing a Linux distribution in UEFI mode. While potential conflicts with a kernel module designed to access system features on Samsung laptops were initially blamed, Matthew Garrett uncovered that the bug was actually triggered by storing too many UEFI variables to memory, and that the bug could also be triggered under Windows as well under special conditions. In conclusion, he determined that the offending kernel module had caused kernel message dumps to be written to the firmware, thus triggering the bug. See also. Notes. References. Further reading: Zimmer, Vincent. Rothman, Michael. Hale, Robert. EFI Architecture. Dr. Dobbs Journal. UBM. Retrieved October 12, 2012. De Boyne-Pollard, Jonathan. The EFI boot process. Frequently given answers. Retrieved October 12, 2012. De Boyne-Pollard, Jonathan. The Windows NT6 boot process. Frequently given answers. Retrieved October 12, 2012. Smith, Roderick W. A BIOS to UEFI transformation. Roderick W. Smith's webpage. Retrieved October 12, 2012. Kathari, Rajiv. UEFI just how important it really is. Hardware Secrets. Retrieved October 12, 2012. Fisher, Doug. UEFI Today, Bootstrapping the Continuum. Intel Technology Journal 15. ISBN A9781934053430. Retrieved September 24, 2013. External links, official website, Intel-sponsored open-source EFI framework initiative. SourceForge. Intel EFI UEFI portal, UEFI documents, Microsoft UEFI support and requirements for Windows operating systems, how Windows 8 hybrid shutdown/fast boot feature works.